In August of 2025, a planet disappeared. Not slowly, not gradually fading into the cosmic
See,
background
this
like a
spike here.
dying star.
Yeah, but what's
It
causing
vanished
it?
It's this new
completely.
variable.
Oh,
In the
I see
span of
now.
8 weeks,
Try
a
adjusting
gas
it.
giant
Behold the
95
majestic
times the
spiral
mass of
galaxies,
Earth,
vast and
a world
beautiful.
large
Their
enough
arms
to
swirl
be
eternally, a
visible
dance
from
of stars and
4.3
dust,
light
cosmic
years
wonder.
away, ceased to exist
The
in our
data is still
telescopes.
unstable.
This wasn't
I see
science
it. We need to
fiction.
adjust the parameters.
This was Alpha
Agreed.
Centauri,
Let's run it again.
our nearest
A
stellar
pleasure.
neighbor,
I'm confident
the
this will be a
brightest star
success.
system in the
Absolutely.
Southern
The
Sky.
potential here
The
is remarkable.
closest
I'm
sun-like
excited to
star
get started.
our own. And what happened there would challenge everything we thought we understood about planets. But to understand how a planet can disappear, we need to start where all good mysteries start, with the question nobody could answer. The night sky above the Atacama Desert is different from anywhere else on Earth. At 13,000 feet elevation, the air is so thin and dry that atmospheric distortion nearly disappears. Stars don't twinkle here, they burn. Constant points of light against absolute black, as if someone punched holes in a velvet curtain and let eternity shine through. On a clear night in the southern hemisphere, Chile, South Africa, Australia, one star outshines nearly all others. A brilliant yellow-white point low on the horizon. To the naked eye, it appears singular, steady, unremarkable except for its brightness. The ancient Greeks called it Alpha Centauri, first star of the Centaur constellation. But they didn't know what we know now. Alpha Centauri isn't one star, it's three. Alpha Centauri A is the largest, a yellow dwarf star 1.1 times the mass of our sun, almost identical in size, temperature, and luminosity. If you could somehow stand on a planet orbiting Alpha Centauri A looking up at its sun, you'd see nearly the same golden disk we see from Earth. Same color, same warmth on your face. You might not realize you were looking at a different star at all. Alpha Centauri B orbits A in a slow gravitational dance. It's smaller 0.9 solar masses, but still substantial. A respectable star in its own right. The two stars circle each other every 80 years, sometimes approaching as close as 11 times the Earth-Sun distance, sometimes separating to about 36 times that span. And then there's Proxima Centauri. Proxima is tiny. A red dwarf star barely 12% the Sun's mass, orbiting the AB pair at an enormous distance, 13,000 times the Earth-Sun separation. It's the closest of the three to us, which is why it carries that name. Proxima, nearest. But Proxima is a hostile place. Red dwarfs are violent stars. They erupt with massive solar flares that would sterilize any nearby planets with radiation. Proxima does have planets. We discovered Proxima b in 2016, an Earth mass world in the habitable zone. But habitable zone is a misleading term when the star itself is trying to kill you. Number. If humanity ever leaves the solar system, if we ever build ships capable of crossing interstellar space, if we ever establish a foothold on worlds orbiting other stars, Alpha Centauri A is the target. The sun-like star, the familiar star, the star 4.3 light years away. 4.3 light years, let that number settle. Light traveling at 186,000 miles per second, fast enough to circle Earth 7 times in 1 second, takes 4.3 years to cross that distance. It's the nearest star system to our own, and it's still incomprehensibly far. With our fastest spacecraft Voyager 1 traveling at 38,000 miles per hour, the journey would take 73,000 years. 73,000 years. Longer than all of recorded human history. But there are proposals. Breakthrough Starshot, a project announced in 2016, envisions tiny laser-propelled probes accelerated to 20% the speed of light. At that velocity, the journey shrinks to 21 years. Still longer than a career. Still longer than most marriages. But within the span of a single human lifetime. 21 years to reach our nearest neighbor. 21 years to discover what's there. And for 40 years, we've been trying to answer that question from here. Trying to see what planets orbit Alpha Centauri A. Trying to understand what worlds exist at our closest stellar destination. For 40 years, we found nothing. Finding planets around other stars is one of the great challenges of modern astronomy. Planets don't produce their own light. They're tiny compared to stars. And they're utterly drowned out by their parent star's overwhelming glare. Imagine standing in New York City at night trying to spot a firefly hovering next to a searchlight in Los Angeles. That's the challenge. Except the searchlight is billions of times brighter than the firefly, and they're separated by a distance so small from your perspective that they appear to occupy the same point in space. For decades, astronomers developed clever indirect methods. The transit method watches for planets passing in front of their stars, causing tiny dips in brightness, like watching a gnat fly across a floodlight. The radial velocity method detects the subtle wobble planets create as they orbit, pulling their stars back and forth through space like a dance partner. These methods worked. We've discovered thousands of exoplanets using these techniques. Hot Jupiters orbiting closer to their stars than Mercury orbits the Sun. Super-Earths unlike anything in our solar system. Ice giants, rocky worlds, ocean planets, a stunning diversity. But for Alpha Centauri A, these methods failed. The transit method requires perfect geometric alignment. The planet's orbit must be tilted edge-on to our line of sight so the planet passes directly between us and the star. Most planetary systems aren't aligned this way. We weren't lucky enough with Alpha Centauri. The radial velocity method struggles with binary star systems. Alpha Centauri on A and B orbit each other, creating massive wobbles that swamp any signal from planets. It's like trying to hear a whisper in a thunderstorm. For 40 years, observation after observation, proposal after proposal, Alpha Centauri A remains silent. No hot Jupiters, no super-Earths, no detectable planets at all. Either the system had no planets, or the planets were hidden beyond our ability to see them. And then in December 2021, everything changed. The James Webb Space Telescope launched on Christmas Day 2021, a decade behind schedule, billions over budget, and representing the most complex and ambitious space observatory ever constructed. Webb is not like Hubble. Hubble orbits 400 miles above Earth's surface, close enough that astronauts could visit and repair it. Webb orbits the Sun nearly 1 million miles from Earth at a gravitational balance point called L2. No human will ever touch it again. Hubble observes primarily invisible and ultraviolet light, the same wavelengths our eyes see. Webb observes in infrared, heat radiation, the glow of warm objects. Why infrared? Because planets glow in infrared. Even if they don't produce their own light, they produce their own heat. Gas giants are warm from leftover formation energy. Rocky planets absorb starlight and re-radiate it as heat. In infrared wavelengths, planets are thousands of times brighter relative to their stars than they are in visible light. It's still like spotting a firefly next to a searchlight. But if the searchlight is dimmer and the firefly is brighter, the task becomes possible. Webb has another advantage, a coronagraph. Hold your hand up and block the sun. Suddenly you can see the sky around it, the faint glow of the solar corona, the brightness of the daytime sky. Your hand acts as a coronagraph, blocking the overwhelming central light source and revealing what's hidden in its glare. Webb's coronagraph is more sophisticated. Tiny mass engineered to nanometer precision, positioned to block starlight, while allowing light from nearby objects to pass through. Combined with Webb's infrared vision, the coronagraph makes direct imaging of planets possible. Not easy, possible. By 2025, Webb had been operational for 3 years. It had revolutionized our understanding of the early universe, peering back to galaxies forming just a few 100 million years after the Big Bang. It had analyzed the atmospheres of distant exoplanets, detecting water vapor, carbon dioxide, methane. It had captured images of star-forming regions with unprecedented clarity, but it had never pointed at Alpha Centauri A. Not for lack of interest, for lack of time. Webb is the most oversubscribed telescope in history. Every astronomer on Earth wants to use it. Observation time is allocated through a brutally competitive proposal process. You submit your scientific case, your technical plan, your analysis strategy. A committee of experts reviews hundreds of proposals and selects the most scientifically valuable. Most proposals are rejected, but in 2023, a team at Johns Hopkins University submitted a proposal. In 2024, they submitted again, both times rejected. In 2025, they submitted a third time. This time, the proposal was accepted. Dr. Evelyn Hartwood spent 2 decades studying exoplanets before Alpha Centauri. 20 years of graduate school, postdoctoral positions, faculty applications, grant proposals. 20 years of telescope time requests, data analysis, paper writing, peer review. 20 years of watching other people make discoveries while her own proposals got rejected. Her own observations came up empty. Her own papers got delayed in the review process. 20 years is a long time to wait for your moment. Hartwood was 42 when the Alpha Centauri proposal was finally approved. She'd been at Johns Hopkins for 6 years. Tenured, respected, productive, but not famous, not a household name, not someone who'd made a discovery significant enough to change the field. She wanted that. She'd always wanted that, but she understood something most scientists learn eventually: wanting isn't enough. Brilliance isn't enough. Hard work isn't enough. You need patience. You need persistence. You need the ability to endure rejection after rejection, failure after failure, and come back for another attempt. And you need luck. In March 2025, Hartwood's luck changed. The email arrived on a Tuesday morning. Subject line, JWST, Cycle 4 Proposal Decision. She'd learned not to get excited by these emails. She'd received too many rejections. She opened it expecting another polite paragraph explaining that, while her proposal was scientifically meritorious, the committee had limited time available and had selected other projects with higher priority. The first word was, congratulations. She read it 3 times. Then she called her collaborator. Dr. Silas Brennan had spent 8 years building the most sophisticated planetary collision simulation code in existence. 8 years of computational physics, numerical methods, parallel processing algorithms. 8 years of running test simulations on university supercomputers, comparing results to known data, refining the math, improving the accuracy. 8 years to create a tool that could model what happens when 2 gas giant planets collide. It seemed like an academic exercise. Planetary collisions are rare. Mature planetary systems like our solar system have been stable for billions of years. The age of violent collisions ended long ago when planets were still forming and their orbits were chaotic. Or so everyone thought. Brennan was 35, MIT, PhD in computational astrophysics. Quiet, methodical, the kind of scientist who speaks rarely but precisely, who lets his code and his results speak for themselves. When Hartwood called him in March 2025 about the approved JWST proposal, Brennan said 3 words, "I'll need time." He meant time on the MIT supercomputing cluster, time to run preliminary models of what they might see at Alpha Centauri, time to understand what different planetary configurations would look like in Webb's infrared cameras. Hartwood gave him 6 weeks. Brennan used 4. He always worked faster than he promised. The observation campaign was scheduled for May 15th through July 10th, 2025. 8 weeks. 6 individual observation sessions, each lasting 4 to 6 hours. Each session required extraordinary precision. Webb had to point at Alpha Centauri A with its coronagraph perfectly aligned. The star had to be centered on the coronagraph mask to within a fraction of an arcsecond, less than 1,000th of a degree. If the pointing drifted even slightly, starlight would leak past the mask and flood the detector, drowning any planet signal. Webb's fine guidance system maintains this precision automatically. A set of sensors continuously monitors the telescope's pointing, measuring drift thousands of times per second and commanding tiny adjustments from the reaction wheels, spinning flywheels that rotate the telescope by conservation of angular momentum. It's a triumph of engineering, but it requires perfect planning. Each observation session is scripted months in advance down to the second. Every telescope movement, every detector exposure, every filter change. Hartwood and Brennan spent April finalizing the observation plan. 6 sessions, multiple rotation angles to distinguish real objects from instrumental artifacts, multiple infrared wavelengths to characterize any detected objects, multiple exposure times to maximize sensitivity while avoiding detector saturation from the bright star. Everything had to be perfect. They wouldn't get a second chance. May 14th, 2025. The night before the first observation. Hartwood couldn't sleep. She lay in bed watching the ceiling, thinking about everything that could go wrong. Equipment failure, software glitch, cosmic ray hit at the wrong moment, detector noise masking a real signal, analysis error, false positive, 20 years to get here, one mistake could waste it all. At 3 in the morning, she got up and made coffee, opened her laptop, reviewed the observation plan for the 100th time, every parameter, every setting, looking for something she'd missed. She found nothing. The plan was solid, but that didn't stop the anxiety. At 7 a.m. Brennan called. "You ready?" "I haven't slept." "Neither have I." A pause. "The math is good, Evelyn. If there's a planet in the detectable range, we'll see it. And if there isn't, then we'll know that too. Either way, we answer the question." That was Brennan, always focused on the science, never the stakes. It was infuriating and comforting in equal measure. "The observation starts at 9 p.m. our time," Hartwood said. "You'll be online. I'll be there. May 15th, 9 p.m. Eastern Time, 2 a.m. Universal Time." Hartwood sat in her office at Johns Hopkins laptop open, connected to the JWST observation monitoring system. Brennan was on video call from MIT. They'd invited no one else. This first observation was theirs alone. The monitoring system showed Webb's status in real time, telescope orientation, target coordinates, coronagraph position, detector temperature, every parameter updating every few seconds. At 9 p.m. exactly, the status changed. Observation in progress. Webb was pointing at Alpha Centauri A. 4 hours of exposure followed. Nothing to see in real time, the raw data was meaningless until processed. Just numbers streaming from the detector, photons converted to electrons, electrons converted to digital counts. But Hartwood watched anyway, watching the numbers scroll, watching the exposure time tick upward, watching the data accumulate. At 1 a.m., the exposure ended. Status changed to slewing to next target. Webb was moving on. The first observation was complete. How long until we see the raw? Brennan asked. Raw data downloads in 4 hours. Processed data by tomorrow afternoon. Can't we process it ourselves? We can try, but the pipeline is complicated. Brennan smiled. It wasn't a warm smile. It was the smile of someone who understands complicated. Send me the raw data when it arrives. The raw data arrived at 5 a.m. Brennan downloaded it immediately. By 8 a.m., he had written custom processing code. By noon, he had preliminary images. He called Hartwood. You need to see this. Her office 30 minutes later. Brennan's laptop on her desk showing a grayscale image. Mostly noise, random, static, bright pixels scattered across the frame. At the center, a black circle where the coronagraph had blocked Alpha Centauri A. And near the edge of that black circle, slightly offset to the upper right, 2 faint smudges. 2 by Hartwood leaned closer. Maybe? Brennan zoomed in. The smudges became clearer clusters of bright pixels. One was stronger, 3 or 4 pixels. The other was barely visible, just 2 pixels brighter than background. Main signal has signal-to-noise ratio 2.3. Secondary signal is 1.5. Both marginal. But they're there. They might be there, or they might be random noise. What's the probability both are random? Brennan pulled up statistics. Main signal alone, 4% chance of being noise. Secondary signal, 15%. Both appearing simultaneously at consistent separations from the star, less than 1%. Hartwood felt her pulse quicken. So this is real. 2 objects. Possibly. We need the next observation to confirm. If they're real planets orbiting the star, they'll stay at fixed positions relative to Alpha Centauri when we rotate the telescope. If they're artifacts, they'll rotate with the telescope. When's the next observation? May 30th, 2 weeks. 2 weeks. 14 days of waiting. 14 days of wondering if those faint smudges were the first glimpse of planets orbiting Alpha Centauri or just random fluctuations in detector noise. Hartwood looked at the image again. 2 faint smudges, maybe 6 pixels total between them. 20 years of work, potentially coming down to 6 pixels. There's something else, Brennan said. He pulled up spectral analysis. Different wavelengths. The main signal appeared in 3 different infrared filters. The secondary appeared in only 1. Main signal has spectral signature, Brennan said. Brighter at longer wavelengths, consistent with thermal emission from a warm object. Secondary signal is too faint to characterize. So the main one is definitely not an artifact. Probably not, but we need rotation confirmation. 14 days, May 30th, 2025. Second observation session. This time, Hartwood invited 2 graduate students from her research group. If this was going to be a discovery, they deserved to be part of it. Same waiting, same streaming data, same 4-hour exposure. But this time, Webb had rotated 30 degrees around its axis. The telescope's orientation relative to Alpha Centauri A was different. Real objects would stay at the same position relative to the star. Artifacts would rotate with the telescope. This was the test, real or artifact. The observation finished at 1 a.m. raw data at 5 a.m. Brennan's preliminary processing by 9 a.m. He called Hartwood. His voice was different this time, tighter. Controlled excitement, barely contained. You need to come to MIT. What did you find? Just come, I'll show you. She caught the 11 a.m. Acela to Boston, 3.5 hours of train staring out the window, trying not to think about what Brennan had found. Trying not to let hope become assumption. MIT campus, 2:30 p.m. Brennan's office in the physics building. He had 3 monitors set up, each showing different images. Left monitor, first observation. The 2 faint smudges upper right of the coronagraph mask. Center monitor. Second observation. 1 bright point of light, same position relative to the star, different position relative to the detector. The secondary signal was gone. Right monitor. Both images overlaid with the star positions aligned. The bright signal from the second observation sat exactly on top of the main signal from the first observation. Hartwood stared. It didn't rotate. It didn't rotate. So it's orbiting the star. Yes. And the secondary signal? Gone. Either it was noise in the first observation, or it faded below detection threshold in 2 weeks. Can planets fade that fast? Not normally, but let's focus on what we have. The main signal is real. He pulled up more data. Signal-to-noise ratio 4.7 in the second observation. Probability of being noise less than 0.01%. Spectral analysis showing clear thermal signature. That's a thermal spectrum, Hartwood said. That's an object glowing from its own heat. Yes, and the spectrum is consistent with a gas giant atmosphere. Methane absorption here, water vapor absorption here. He pointed to specific wavelengths. This is a planet. They sat in silence for a moment. 20 years. How big? Hartwood asked. Rough estimate from the brightness and spectrum somewhere between Saturn and Jupiter mass. Call it zero point 0.9 to 1.1 Saturn masses. Distance from the star. Angular separation is 430 milliarseconds. At Alpha Centauri's distance, that's 2.7 astronomical units, about 400 million kilometers. Orbital period. Brennan pulled up a calculation. Using Kepler's third law, assuming Alpha Centauri A has 1.1 solar masses, a planet at 2.7 astronomical units would have an orbital period of about 3.5 years. 3.5 years. Longer than Hartwood's tenure at Johns Hopkins. Longer than Brennan had been working on his simulation code. But they'd found it. They'd actually found it. We need the other 4 observations to be sure, Brennan said. Confirm the orbital motion. Rule out background contamination. Get better spectral measurements and understand what happened to that secondary signal. When's the next one? June 15th. June 15th, third observation session. The signal was stronger. Signal-to-noise ratio, 5.1. The position had shifted slightly, consistent with orbital motion around Alpha Centauri A. The spectrum was clearer, showing more detailed absorption features. But there was something else, something unexpected. The brightness had decreased, not dramatically but measurably. The signal was about 15% dimmer than the second observation 2 weeks earlier, and the secondary signal had not reappeared. Is that normal? Hartwood asked. For a planet, no. Brennan pulled up theoretical models. Planets are thermally stable. Their brightness shouldn't change significantly over weeks or months. Could it be atmospheric variation? Storms, cloud patterns? Gas giants do have weather. Jupiter's brightness varies by a few percent as different atmospheric features rotate in and out of view. But 15% in 2 weeks, he shook his head. That's unusual. What about the secondary signal from the first observation? If it was real and not noise, and if it faded this much faster than the main signal, Brennan ran calculations. It would be completely undetectable now. But I don't have an explanation for why 2 objects would both be fading. Should we be worried? I don't know. Let's see what the next observations show. June 30th, fourth observation. The signal was there. Consistent position. Spectrum still matching a gas giant atmosphere. But dimmer again, now 18% below the peak brightness from May 30th. The secondary signal remained absent. July 10th, fifth and sixth observations back-to-back sessions 8 hours apart. Both showed the main signal. Both showed continued dimming, now 22% below peak. Something was happening to the planet. Some process was reducing its infrared brightness, gradually but steadily over the course of 8 weeks. And the secondary object, if it had ever been real, was gone completely. Could the main planet be moving away from us? One of the graduate students asked. Changing distance. The orbital motion is only about 20 degrees over 8 weeks, Brennan said. Distance change would be less than 5%. Not enough to explain 22% brightness drop. Cooling. Possible. If the planet is young and still contracting, it's radiating away its formation heat. As it cools, it gets dimmer. But young planets cool over millions of years, not weeks. Atmospheric haze. That's more plausible. If something triggered formation of high-altitude hazes, photochemistry, seasonal changes. The hazes could block infrared emission. We see that on Titan, Saturn's largest moon. They ran models, haze formation, seasonal variations. None quite fit the observed brightness drop. We're missing something, Hartwood said quietly. The planet is telling us something, and we're not understanding it. Brennan was staring at his laptop, running calculations. Evelyn, look at this. He'd plotted the brightness measurements over time. 6 points, one for each observation session from May through July. The decline wasn't linear. It was exponential, a curve, not a straight line. If this trend continues, Brennan said slowly, the planet would be completely undetectable by late September. A chill ran through the Hartwood's chest. What could cause exponential fading? I don't know, but we need to report what we've found. Planet detected brightness declining secondary signal, possibly present initially but unconfirmed. We present the data honestly and let the community evaluate it. And they spent 3 weeks on intensive analysis, extracting every piece of information from the data, measuring the planet's position in each observation, tracking its orbital motion, analyzing the spectrum at every wavelength, identifying absorption features, comparing to atmospheric models, calculating the signal-to-noise ratio, estimating the probability of false positive. They checked everything, cross-referenced with star catalogs to rule out background stars, compared to deep sky surveys to rule out distant galaxies, analyzed instrumental artifacts and other Webb observations to understand what false signals look like. Every test came back clean for the main signal. This was a real object, orbiting Alpha Centauri A, with properties consistent with a gas giant planet. The secondary signal from the first observation remained ambiguous, too faint to confirm, too intriguing to ignore completely. By the end of July, they had their numbers. Mass 0.9 to 1.1 Saturn masses. 95 times Earth's mass. Orbital separation 2.7 astronomical units. 400 million kilometers. Orbital period 3.5 years. Temperature 600 to 900 Kelvin. Hot for a gas giant suggesting youth. Statistical confidence 5 sigma. 1 in 3.5 million chance of being a false positive. Brightness decline 22% over 8 weeks. Exponential decay pattern. Cause unknown. Secondary signal possible detection in first observation only. Unconfirmed. We should publish, Brennan said. Hartwood hesitated. The brightness drop, the secondary signal, people will question it. We report it. We acknowledge we don't understand it. That's honest science. Some people will use that uncertainty to dismiss the whole detection. Some people will question it anyway. That's how science works. Brennan looked at her. Evelyn, you've been waiting 20 years for this. The data is solid. The detection is real. Don't let fear of criticism stop you from announcing what you found. He was right. She knew he was right. Okay, she said. We publish. They submitted the paper to Nature on August 1st, 2025. Title, A Saturn Mass Planet Orbiting Alpha Centauri, Detected via Direct Infrared Imaging. The abstract mentioned both the confirmed detection and the mysteries. We report the discovery of a Saturn mass planet orbiting Alpha Centauri A at 2.7 astronomical units. The planet shows unexpected brightness, variability declining 22% over 8 weeks. A possible secondary object was marginally detected in initial observations, but not confirmed in subsequent sessions. These features require further investigation. Nature's editors fast-tracked the paper, sent it to 5 expert referees within a week. While waiting for reviews, Hartwood and Brennan decided to announce the discovery publicly. Major findings should be shared immediately, not held back for months during publication. On August 1st, 2025, Johns Hopkins University issued a press release. Astronomers discover planet orbiting Alpha Centauri A. The response was immediate. Within 6 hours, the story was on CNN and in BBC, New York Times, Washington Post. Every major news outlet covered it. Gas giant found orbiting nearest sun-like star. Alpha Centauri planet discovery marks milestone in exoplanet science. Our stellar neighbor has a planet and it changes everything. Twitter exploded. Hashtag Alpha Centauri. Planet trended worldwide. Elon Musk tweeted, first confirmed exoplanet at our nearest stellar neighbor. Starship's destination. Thousands of retweets. Neil deGrasse Tyson. If confirmed by independent observations, this is the most significant astronomical discovery in decades. Alpha Centauri isn't just nearby, it's our potential future. The Breakthrough Starshot team issued a statement. This discovery fundamentally changes the mission. We now have a confirmed target to study. Space agencies noticed. NASA issued congratulations. ESA did the same. Private calls started happening behind the scenes. What would a mission to Alpha Centauri look like? For 3 days, Hartwood lived in a whirlwind of media requests, interviews, congratulations, emails. On August 4th, she finally went home. Exhausted, overwhelmed. She sat on her couch and let the silence settle. 20 years. All the rejected proposals, all the failed observations, all the moments of doubt. All of it led here. She discovered a planet orbiting Alpha Centauri A, the nearest sun-like star. Her name would be in textbooks, in the history of astronomy. Forever. She closed her eyes, just for a moment. Pure satisfaction. Then her phone rang, Brennan's name on the screen. She answered, Silas what? Evelyn. His voice was tight, controlled, the way it got when something was very wrong. We have a problem. Her stomach dropped. What happened? I just got an email from Klaus Vandenberg at ESO. His team got JWST, time to confirm our detection. They observed last week. Same instrument, same configuration. Hartwood's pulse quickened. And a long pause. Evelyn, the planet's gone. Gone. The words sat between them like a physical thing. Heavy. Undeniable. What do you mean gone? Hartwood's voice came out steady. Clinical. The professional mask she'd learned to wear over 2 decades of setbacks. Define gone. I mean, there's nothing there. Brennan's voice crackled through the phone. Vandenberg's team observed Alpha Centauri A on October 15th. Same JWST near-infrared camera. Same coronagraph configuration. Same exposure time. They processed the data using the same pipeline we did. And empty field. No signal. No point source. Nothing at the position where we detected the planet. Nothing anywhere in the search region. Hartwood stood up, sat down, stood up again, her mind racing through possibilities, explanations, anything that made sense. Send me their data. Already forwarding it. But Evelyn, send me everything. Raw data processed images, their analysis notes, everything. I will, but you need to understand what this means. People are going to say, I know what people are going to say. Send me the data. The email appeared 30 seconds later. 7 attachments. Gigabytes of FITS files. I'm going to the office, Hartwood said. Meet me online in 1 hour. She hung up before Brennan could respond. 1 a.m. Hartwood's office at Johns Hopkins. 2 monitors glowing in the darkness. Brennan on video call from MIT. Neither of them had changed clothes since the phone conversation 6 hours ago. On screen, 2 images side by side. Left Hartwood's detection from May 30th. The bright point source signal-to-noise ratio 4.7 unmistakable against the background. Right Vandenberg's observation from October 15th. Same field of view, same coronagraph mass blocking the star, same infrared wavelength, and nothing. Just noise. Random bright pixels scattered across the detector. No concentration, no pattern, no signal. Run the statistics, Hartwood said. Brennan pulled up analysis code. Background noise in Vandenberg's data is actually slightly lower than ours. Detector was performing better. If the planet were there at the same brightness we saw, signal-to-noise ratio would be 5.2. So they should have seen it more clearly than we did. Yes. And they saw nothing. Correct. Hartwood leaned back. Instrumental failure. Something wrong with Webb during their observation. I checked the engineering telemetry. All systems nominal. Pointing stable. Temperature normal. No anomalies. Data processing error. I replicated their pipeline. Got the same result. No signal. Background object that happened to be at the same position during our observations. We checked star catalogs. Nothing there. And a background object wouldn't have moved with Alpha Centauri through our 6 observations. Hartwood rubbed her eyes. 2 a.m. now. 22 hours without sleep. Walk me through orbital mechanics, she said. May 30th to October 15th is 20 weeks. Where should the planet be? Brennan pulled up a simulation, Alpha Centauri A at center. The planet's predicted orbit drawn as an ellipse. 20 weeks is roughly 1/6 of the orbital period, about 60 degrees of motion. He advanced the simulation. The planet moved along its arc. The planet should have moved from here to here. Or could it have passed behind the star? Only if the orbit is nearly edge-on to our line of sight. Probability less than 5%. And even then, occultation would last weeks, not months. We're now 4 months past the original detection. 4 months, August to December. If they could get another observation slot. What about the brightness decline we saw, Hartwood asked. 22% drop over 8 weeks. Exponential decay. If that continued, Brennan ran numbers. To go from our July brightness to completely undetectable would require 97% brightness decrease total. In 10 weeks. Yes. No known atmospheric process does that. No, Brennan paused. Unless it's not an atmospheric process. They sat with that thought. You're thinking about the secondary signal, Hartwood said. I'm thinking about what it would mean if both signals were real. 2 objects, both fading. One disappeared after 2 weeks. The main one took 10 weeks. What kind of phenomenon produces that pattern? I don't know. Neither do I, but it's not simple planetary behavior. Hartwood stared at the empty image, the place where a planet should have been. Vandenberg's going to publish, Brennan said quietly. Let him. We report what we saw. He reports what he saw. Both datasets are real. The conclusion people will draw: some people will think we made a mistake. Others will want more data. We'll request another observation. We'll figure out what happened. Brennan didn't respond immediately. When he did, his voice was softer. You know what this is going to look like. She knew. The planet that wasn't there. The discovery that disappeared. 20 years of work. 3 days of triumph. And now this. I'm going home, Hartwood said. We'll deal with this tomorrow. She closed the laptop. The media reversal was swift and brutal. August 1st through 4th, discovery of the century. Headlines worldwide. Hartwood's name everywhere. October 20th, Alpha Centauri planet not seen in follow-up observations. October 21st, questions mount over vanishing exoplanet. October 22nd, did Alpha Centauri planet ever exist? The articles were carefully neutral. Apparent non-detection. Results require independent verification. Scientific debate ongoing, but the subtext was clear. Twitter was less subtle. At Astroskeptic, another premature exoplanet claim bites the dust. When will they learn? At Science Watchdog? This is why peer review exists. Hartwood deleted Twitter from her phone after the second day, stopped reading news sites, but she couldn't escape it completely. Colleagues who suddenly had urgent business elsewhere when she approached. The department chairs chat about managing expectations and institutional reputation. On October 25th, her phone rang. Theodore Ashford. Ashford was 68, Harvard-Smithsonian Center, one of the giants of exoplanet science. He'd been Hartwood's postdoctoral advisor 15 years ago. He'd also made one of the most famous false detections in the field's history, 2012. Ashford's team announced a super-Earth orbiting Tau Ceti using radial velocity, 3 independent data sets all showing the same signal. High confidence. 6 months later, another team proved the signal was stellar activity, not a planet. Ashford published a retraction, but the damage to his reputation took years to repair. Now he was calling Hartwood. Evelyn, how are you holding up? I've been better. I saw Vandenberg's results and the coverage. Hartwood said nothing. I'm calling because I know what you're going through. I've been exactly where you are. A pause. You didn't do anything wrong. The words hit harder than expected. Her throat tightened. You did careful work, Ashford continued. Proper methods. You reached a conclusion supported by your evidence. That's good science. The planet's gone, Theodore. Yes, and that's surprising, but surprising doesn't mean you were wrong to report what you saw. It means nature is more complicated than we thought. The scientific community, the actual scientific community, the people who matter, they're waiting for more data. They want to understand what's happening, not just dismiss it. Vandenberg is publishing a non-detection paper. So publish a response, acknowledge the non-detection, propose explanations, request more observations. That's how science works. Hartwood closed her eyes. What if it never comes back? Then you report that. You present the data honestly. You acknowledge the mystery. A pause. Melissa, do you know what I regret most about my false detection? What? Not the mistake. Mistakes happen. I regret becoming defensive, seeing challenges as attacks instead of staying curious. His voice was quiet. The stellar activity that mimicked a planet signal taught us important things about stars. But I was too focused on defending my claim to appreciate that. So what are you saying? Stay curious. Whatever's happening at Alpha Centauri, it's interesting. Treat it like a puzzle, not like a threat to your reputation. After they hung up, Hartwood sat in the quiet. Ashford was right about the science, about the approach. But being right didn't make it hurt less. November 5th, 2025. Vandenberg published in Astronomy and Astrophysics. Title: No Evidence for a Planetary Companion to Alpha Centauri. In October 2025, JWST Observations. The paper was diplomatic until the final sentence. We urge the community to require independent confirmation before accepting direct imaging detections as confirmed discoveries. It was a direct criticism. Polite but pointed. Hartwood read it twice, then called Brennan. You saw Vandenberg's paper. Yeah, we need more observations. Already drafting a proposal for director's discretionary time. Director's discretionary time was for urgent time-sensitive observations, supernovae, asteroid impacts, unexpected events. Did a vanishing planet qualify scientific justification? Hartwood asked. We detected a variable infrared source. Brightness declined exponentially, then apparently vanished. That variability is scientifically interesting regardless of interpretation. We need more observations to understand the phenomenon. When can you submit? Tomorrow. Brennan paused. Evelyn, I need to tell you something. The tone made her alert. What? I went back through our original data, looking at that secondary signal from the first observation. He sent an image, enhanced, zoomed. The first observation from May 15th, two signals clearly visible. The main one they'd focused on, and the secondary much fainter, about half an astronomical unit farther from the star. Signal to noise 1.5, Brennan said. We noted it but didn't claim a detection because it didn't appear in subsequent observations. We thought it was noise. But what if it wasn't? What if both signals were real objects that both faded? The secondary disappeared in 2 weeks. The main one took longer but followed the same pattern. Two objects both fading exponentially. That's not normal planetary behavior, but it might be something else. A new possibility opening. Submit the proposal, Hartwood said. We need more data. The proposal was approved November 20th, 40 hours of observation time spread across December and January. Multi-wavelength, multiple coronagraph configurations. Every check against instrumental artifacts. One condition, immediate public data release. No proprietary period. The message was clear. This is important but controversial. The community needs transparency. Hartwood accepted without argument. December 5th, 2025. First observation of the new campaign. Hartwood, Brennan, and 3 other team members online. Watching, waiting. 4 hours of exposure. Data download. Processing. 9 a.m. Eastern. Brennan's preliminary reduction appeared. A signal. Faint. Signal to noise 1.9. Right at the detectability edge. Brightness 35% of the May peak. It's back, one of the graduate students whispered. Maybe, Brennan said carefully. Statistical confidence isn't high enough. Could be noise. Next observation. December 7th, 48 hours. December 7th, second observation. Nothing. Empty field. Background noise only. The graduate student who'd been excited looked devastated. This is why we keep observing, Hartwood said quietly. One data point tells us nothing. December 20th, third observation. A signal. Stronger. Signal to noise, 2.8. Brightness 42% of original peak. But the position was wrong, offset by 3 arcseconds, nearly 900 million kilometers at Alpha Centauri's distance. That's impossible, Brennan said. No planet moves that far in 2 weeks. Unless it's not a planet, Hartwood said slowly. Everyone looked at her. We've been assuming one object in a stable orbit. But what if it's not one object? What if it's multiple objects or an extended structure or something we don't have a category for? Brennan pulled up simulations. An extended structure could explain variable brightness, different parts visible at different times. Could explain position offsets, we're seeing different components. Like what rings? Rings don't glow this bright in infrared, but a debris cloud could. Hot dust from a collision or disruption event. The word hung there. Collision. Keep going, Hartwood said. December 24th, fourth observation, Christmas Eve. Hartwood was alone in her office. Everyone else with family. She'd volunteered to monitor solo. Truth was, she preferred being here. Working, not thinking about empty apartments. Exposure finished 11 p.m. Data downloaded. Processing complete at midnight. Christmas Day. 0 hours, 0 minutes. A signal. The brightest since original observations. Signal to noise 3.1. Brightness 47% of peak. She stared at the screen, then checked the schedule. Next observation in 6 hours. Same configuration. She decided to wait. Watch both. Compare them directly. 6 hours passed. Second Christmas observation completed. Processing finished. Hartwood looked at the result. Same position. But brightness had dropped to 15%. In 6 hours, while the same telescope looked at the same star, the object lost 2/3 of its brightness. She sat very still. That wasn't orbital motion. That wasn't atmosphere. That wasn't any planetary phenomenon she knew. She called Brennan. It changed in real time. What? The brightness, between two observations 6 hours apart, dropped from 47% to 15%. Silence. Then that's not possible. The data says it happened. Send it to me. She did. Heard him typing. Confirmed, he said finally. Signal to noise dropped from 3.1 to 1.4 in 6 hours. What does that mean? I don't know, but I'm going to run collision simulations. New models, See if anything matches this behavior. January 3rd, 2026. Fifth observation. No signal. Below detection threshold. January 10th. Sixth observation. Faint signal. 15% brightness. January 15th. Seventh and final observation. Signal. 38% brightness. Position offset 2 arcseconds from December 20th. Hartwood and Brennan compiled everything. Original 6 observations. Vandenberg's non-detection. 7 new observations. 14 data points spanning 8 months. Brightness versus time looked like random scatter. Position versus time clustered around 2 regions, separated by about 1 astronomical unit. 2 sources, Brennan suggested, or 1 extended source with 2 bright regions. I've been running collision simulations for 3 days, Brennan said. Hundreds of variations, different impact velocities, angles, planet masses. And most don't match, but there's one class that comes very close. He pulled up a video. 2 gas giant planets orbiting Alpha Centauri A, stable for billions of years. Then gravitational perturbation, probably from Alpha Centauri B, during close approach destabilizes the orbits. The orbits become eccentric, chaotic. The planets' paths begin crossing, and then they collide. The video showed it in slow motion. 2 Saturn mass planets, impact velocity 5 kilometers per second. Glancing below. Atmospheres compress heat to thousands of degrees. Material ejected in all directions. Pause at impact plus 1 week. Massive debris cloud glowing bright in infrared. Extended structure. Irregular shape. Multiple bright clumps. Impact plus 4 weeks. Debris expanding, cooling. Overall brightness decreasing. Impact plus 8 weeks. Significantly dimmer. More dispersed. Impact plus 12 weeks. Multiple fragments visible. Different brightnesses. As debris rotates and tumbles, different fragments come into view at different times. The next 6 months. Debris evolving, expanding, cooling. Sometimes bright clumps visible. Sometimes nothing above detection threshold. Position of maximum brightness shifting as different cloud parts rotate. It matched. Not perfectly, simulations never do. But the pattern was there. Flickering brightness, position offsets, gradual dimming, all consistent with observing a collision debris field. Hartwood watched 3 times. When would the collision have happened, Brennan calculated, based on brightness evolution and thermal models impact around late May or early June 2025, when we started observing. Yes. So our first detection was the debris cloud at peak brightness, 1 to 2 weeks post-impact. By October, debris cooled and dispersed enough to be undetectable at Vandenberg's wavelengths. And the flickering now. Different parts of the expanding field rotating in and out of view. It fit every observation, every anomaly, because it wasn't a planet. It was a cosmic catastrophe witnessed in real time. They sat in silence. We didn't discover a planet, Hartwood said slowly. We discovered a planetary collision. If the simulation is right. Is it right? Brennan showed comparison plots. Observed brightness versus simulated. Observed positions versus simulated fragment locations. Correlation 94%. It's right, he said. They spent 2 weeks writing. Title, Evidence for a Recent Planetary Collision in the Alpha Centauri, a System Analysis of Variable Infrared Emission. The paper was careful, presented collision as leading hypothesis. Acknowledged uncertainties. Discussed alternatives, dust obscuration, atmospheric phenomena, and explained why each was less likely. 47 pages, 23 figures, detailed simulation methods, comprehensive uncertainty analysis. They submitted to the Astrophysical Journal on January 25th. No press release, no public announcement, just submitted and waited. But word got out anyway. But February 3rd, email from the journal editor, Dr. James Morrison. Morrison was a legend, harsh critic, demanding standards, famous for rejecting extraordinary claims. The email was brief. Dr. Hartwood, handling your paper personally, sent to 5 referees, expect significant scrutiny. Reviews in 6 weeks. 6 weeks of waiting. Hartwood threw herself into other work. Teaching, grant proposals, anything to avoid obsessing. But every day she checked email. March 15th, 2026. Reviews arrived. Referee 1, compelling. Collision hypothesis explains otherwise inexplicable observations. Need more detailed debris modeling. Major revision. Referee 2, either groundbreaking or creative noise reinterpretation, lean toward former, toned down certainty, major revision. Referee 3, Data analysis sound, hypothesis bold but well supported. Some December-January detections marginal. Be explicit about robustness. Minor revision. Referee 4. Skeptical. Asking us to believe we witnessed one of the rarest events at the nearest star exactly when observing. Probability seems vanishingly small. Not convinced alternatives adequately ruled out. Reject. Referee 5. Collision is one possible explanation not proven. Authors present it as only viable interpretation too strong. Reframe as possible scenario rather than confirmed. Major revision. Could be acceptable after revisions with substantial hedging. Morrison's decision. Major revisions. Address all comments, particularly soften certainty. Present collision as leading hypothesis not proven fact. Better uncertainty analysis. 3 weeks. 4 out of 5 favoring eventual publication. Morrison overruled the rejection. Hartwood read it 3 times. The rejection from referee 4 stung, but they had a path forward. She called Brennan. We got the reviews. And major revisions, but publishable if we hedge the language. How much hedging? Every we detected a collision becomes consistent with a collision scenario. That's science. I know, but frustrating. We know this is what happened. We believe this is what happened based on available evidence. That's different. He was right. He was always right. 3 weeks of 18-hour days, revising every sentence, replacing definitive statements with careful language, expanding uncertainties, adding more alternative explanations. The paper grew to 47 pages. April 6th, they resubmitted. Morrison fast-tracked second review. 2 weeks. 4 accepted. Even referee 4 withdrew objection. While I remain skeptical, authors have addressed concerns. Revised paper appropriately cautious. Accept. Morrison's final decision, April 25th. Accepted for publication, publication date June 1st. 11 months after the original detection. 10 months after the vanishing. 7 months after the collision hypothesis. Finally an answer, June 1st, 2026. The paper appeared online at midnight Universal Time, 9 p.m. Eastern. Hartwood at Johns Hopkins. Brennan at MIT, video connected. Watching the download counter increment. 10 downloads first minute, 50 by minute 5, 200 by minute 10. Within an hour, responses appeared on Twitter. Not journalists, scientists. At Exoplanet Experts, Hartwood/Brennan collision paper. If this holds, rewrites planetary system dynamics understanding. At Astrophysics Prof, bold but well supported. Simulation match striking. Need independent verification. Even skeptics were measured. At Astroskeptic, still unconvinced but revised paper much better, acknowledges uncertainties. Good science. By morning, mainstream media picked it up, but different tone from August. Scientists proposed planetary collision at Alpha Centauri. Vanishing planet mystery may be solved. Not triumphant announcements. Careful reporting. May in every headline. Hartwood appreciated the humility. Science wasn't about certainty. It was about drawing reasonable conclusions from evidence while admitting what you didn't know. And there was still much they didn't know. June 15th, email from Klaus Vandenberg. Subject Alpha Centauri follow-up. Hartwood hesitated before opening it. Vandenberg's non-detection had triggered everything falling apart. The email was short. Dr. Hartwood, I've read your collision paper with great interest. The hypothesis is compelling and explains the variability I missed. I reanalyzed my October data looking for faint extended emission as your model predicts. Found marginal signal too weak to claim detection alone, but consistent with diffuse debris at your predicted brightness. I should have looked for this originally. The oversight is mine. I'm proposing JWST observations for this year to search for the debris cores. Your simulations predict 2 remnant cores should exist stripped of atmospheres, but intact. Finding them would strongly support your hypothesis. Would you be interested in collaborating? Klaus Hartwood showed it to Brennan. He wants to collaborate, Brennan said, after the non-detection paper. Science transcending egos. What do you think? I think we say yes. We need independent observations. His team has different methods, different perspectives. She typed, Klaus, thank you for the reanalysis. Collaboration would be valuable. Let's discuss strategy. The core search became the focus. Brennan's simulations made specific predictions. 2 remnant cores should exist. One about 0.41 Saturn masses, the other 0.58, combined 0.99 Saturn masses matching the original estimate. But cores would be dim, stripped atmospheres, no longer generating significant heat, radiating only faint thermal emission and far infrared. Finding them required different wavelengths, longer wavelengths. JWST's mid-infrared instrument, MIR-A, operating at 25 to 28 microns instead of the 3 to 5 used originally. At those wavelengths, cooler objects glowed brighter. Vandenberg submitted the proposal in July. 80 hours of JWST time, the largest single allocation ever for Alpha Centauri. Approved in August, observations September through December. 3 teams coordinated. Hartwood, Brennan, Vandenberg. Different strategies, different filters, different integration times. September, faint signals at detectability edge. Could be cores, could be noise. October, more faint signals. Positions roughly matching simulation predictions. Still marginal. November, clearer signals. 2-point sources separated by 1.1 astronomical unit. Faint but present in multiple observations. December 18th, 2026. Final session. Longest integration. Best signal to noise. Hartwood at Johns Hopkins. Brennan at MIT. Vandenberg at ESO headquarters in Garching, Germany. Video conference. Processed data appeared 2 a.m. Eastern, 8 a.m. Germany. 2 bright points on screen. Signal to noise ratios 4.2 and 3.8. Clear detections. Vandenberg spoke first. Voice quiet. Careful. I believe we have found them. Brennan ran position measurements. Separation from Alpha Centauri, a core 1 at 1.8 astronomical units, core 2 at 2.9 astronomical units. Separation between cores 1.1 astronomical units. He pulled up the collision simulation. Advanced to 18 months post-impact. Predicted core positions matched observations. Hartwood felt tension release. Tension she'd carried 16 months since the planet's gone. They'd found them, remnants of 2 worlds that collided while humanity watched. Mass estimates, Vandenberg asked. Brennan ran photometry. Core 1 0.41 plus or minus 0.03 Saturn masses. Core 2 0.58 plus or minus 0.04. The simulation predicted exactly 0.41 and 0.58. Combine 0.99 plus or minus 0.05 Saturn masses. The original planet detection, 0.9 to 1.1 Saturn masses. Perfect match. Silence. 3 scientists in 3 countries, understanding what it meant. Not one planet that disappeared. 2 planets, a binary system orbiting each other while orbiting Alpha Centauri A that collided. The original detection was combined light from both plus debris at peak brightness. The flickering was evolving debris. The cores were what remained. We need to publish this, Vandenberg said. Together, Hartwood added. Joint paper, all 3 teams. Brennan nodded. Agreed. The joint paper took 2 months. Hartwood, Brennan, Vandenberg, 12 other co-authors. 3 institutions, 2 continents. Titled Discovery of 2 Planetary Cores in the Alpha Centauri, a system remnants of a recent giant planet collision. Submitted to Nature. The journal that fast-tracked Hartwood's original paper. This time review was smooth. Evidence overwhelming. Multiple independent observations. Clear core detections. Masses matching predictions. Positions matching simulations. Accepted March 2027 with minor revisions. Publication May 1st, 2027, almost exactly 2 years after first detection. A response was immediate and overwhelming. Not controversial anymore. This was confirmation, proof. Cores found exactly where collision hypothesis predicted. Within a week, 15 teams requested JWST, time for Alpha Centauri. Study debris evolution. Search for smaller fragments. Look for surviving moons. Analyze collision dynamics. The Alpha Centauri collision became the most studied event in exoplanet science. Papers appeared rapidly. Spectroscopic analysis of debris composition. Orbital dynamics of binary planets and stellar binaries. Collision rate estimates in multi-star systems. By summer 2027, citations reached 150, fall 200, December 247. One of the most cited astronomy papers of the decade. October 2027. Hartwood received an invitation. The International Astronomical Union Special Session on Planetary Collisions. Cape Town, South Africa. They wanted her keynote. She'd never given a keynote. Dozens of conferences attended, posters presented, contributed talks, but never keynote. She accepted. January 15, 2028, Cape Town International Convention Center. 3,000 astronomers from 90 countries. Hartwood backstage, heart pounding, mouth drawboy, Brennan in audience, Vandenberg. Ashford. Hundreds following the story for 2.5 years. Introduction finished. Applause. Her cue. She walked on stage. Title slide, The Alpha Centauri Collision Discovery Controversy and Confirmation, she began. In May 2025, we thought we'd discovered a planet. By October, we thought we'd made a mistake. By January 2026, we didn't know what we'd found. Today, I'm going to tell you what we know now. 50 minutes, she walked through the entire story. Original detection, brightness drop, vanishing, flickering, collision hypothesis, core discovery. She showed data, simulations, before and after images, comparison plots, 94% correlation. She talked about energy release 10 to the 32nd joules, debris cloud size larger than Jupiter's orbit, timescale billion-year process culminating in one moment, and what it meant. We used to think planetary systems were static. Planets form, settle into stable orbits, stay that way for billions of years. Chaos and collisions end early. After that, silence, stability. Alpha Centauri tells us that's wrong. Planetary systems are dynamic, evolving. Even after billions of years, gravitational perturbations can destabilize orbits. Binary companions can nudge planets into crossing paths. Collisions happen not just in chaotic youth, but in mature middle age. We witnessed this, 4.3 light-years away. A collision occurring June 2020, light reaching us June 2025, exactly when we looked with the most powerful infrared telescope ever built. Some call this incredible luck. I think it's something else. You say, we looked at our nearest neighbor with our best instruments and found violence. Not because violence is rare, but because we finally had tools to see it. I believe planetary collisions happen constantly throughout the galaxy. We've just never had capability to detect them before. New slide, 12 other star systems with possible collision signatures. Since our paper, 4 other collision candidates identified. Young debris disks with chemical signatures of vaporized rock. Infrared excesses varying year to year. Systems with odd mass distributions suggesting recent upheaval. Alpha Centauri wasn't unique. It was the first we had eyes to see. Final slide. Image of 2 cores. Faint points against black. These are the survivors. 2 rocky, icy cores, each larger than Earth, stripped of atmospheres, locked in slowly decaying orbit. Our simulations show they'll merge in approximately 47,000 years. When they do, they'll create a new collision, new debris, new chapter in Alpha Centauri's violent evolution. We won't see it, but 47,000 years from now, if humanity or its descendants still observe stars, they'll witness that merger. They'll study it as we studied this one. And they'll understand, as we now understand, that planetary systems aren't eternal and unchanging. They're living, dying, evolving. Violent on timescales longer than civilizations, but violent nonetheless. Pause. Auditorium silent. I want to end by saying something about failure and persistence. This discovery didn't feel like discovery while happening. It felt like failure. The planet disappeared. Follow-up contradicted initial results. Media turned. Colleagues questioned methods. For months, I thought my career might be over. But failure is only permanent if you stop asking questions. We kept observing, kept analyzing, kept proposing hypotheses and testing them. Not because we were certain we'd find answers, but because not knowing was more interesting than giving up. Eventually, data told us a story, not the expected story, not a simple planet in stable orbit, but something richer, stranger, more violent. A story about 2 worlds dancing together for billions of years before their final catastrophic embrace. That story was worth the failure, worth the doubt, worth the patience. So to everyone who's experienced failed observations, contradictory results, data that doesn't make sense, keep going, keep questioning, keep being willing to be wrong if it means getting closer to being right. The universe has no obligation to make sense to us quickly. But if we're patient, if we're humble, if we let data surprise us, it will eventually reveal truths more beautiful than anything we imagined. Thank you. Applause before she finished. 3,000 people standing. She stood there absorbing it, not the applause itself, but what it represented. Acceptance, vindication, recognition the work was worth it. 20 years from first exoplanet research to this moment. Worth every rejection, every failed proposal, every sleepless night. Worth it. After people crowded around, questions, congratulations, collaboration requests, Brennan found her during a gap. Good talk. You wrote most of the simulation slides. You delivered them well. He hesitated. There's something I haven't told you. What? I've been analyzing core orbital dynamics, long-term evolution models. And the merger won't happen in 50,000 years, more like 47,000. And when it does, energy release will be larger than the first collision because cores are denser, impact velocity higher. So, so if humanity's still around, still observing, we should leave a note in the archives. Flag this system for observation in 47,000 years. Make sure someone's watching. Hartwood smiled. You want to leave a note for astronomers in the year 49,000? Why not they'll thank us, assuming they can read our formats. Fair point. Brennan pulled out his phone, doing it anyway, uploading to IAU archives. Predicted merger event Alpha Centauri, a core circa 49,000 CE. Recommend high cadence infrared monitoring beginning 48,900 CE. He typed, then looked up. Done. Our message to the future. Hartwood felt something shift. The work wasn't just about now, it was contributing to ongoing conversations spanning generations. They'd found something understood, something passed knowledge forward. That was the point. Not personal glory, not vindication, contributing to accumulated understanding. Come on, Brennan said. Vandenberg wants to buy us dinner. European custom requiring celebration of successful collaborations. They walked toward the exit, conference noise fading. Outside, southern sky visible. Clear night, Alpha Centauri brilliant on the horizon, 4.3 light years away. Right now, this moment, debris field expanding. Two cores orbiting, slowly spiraling inward. In far infrared, the system glowed faintly warm remnants of catastrophic violence. Hartwood thought about photons. Light emitted from those cores today would reach Earth in 2032. 4 years from now, someone would point a telescope then. Maybe someone inspired by this discovery. Maybe someone not yet born. They'd see the system's next evolution phase. Cooler debris, wider core separation, different dynamics. And they'd build on this work. Refine models, understand the collision better, ask new questions. That was science's beauty. It didn't end. Every answer generated new questions. Every discovery opened new frontiers. The Alpha Centauri collision would be studied for decades, centuries, as long as humanity looked at stars. And someday, thousands of years from now, when cores finally merged in their second collision, astronomers would watch. They'd have better instruments, better simulations, better understanding. But they'd remember the story started here. 3 scientists in 2025 pointing a telescope at the nearest star, finding something unexpected, having patience to understand it. Worth remembering. Worth the 20 years. June 2029. Breakthrough Prize in Fundamental Physics Ceremony, San Francisco. Most prestigious award in physics. $3 million. Hartwood, Brennan, Vandenberg on stage together. Citation. For discovery and characterization of the first planetary collision in an exoplanetary system, demonstrating that planetary systems undergo violent evolution throughout their lifetimes, and opening the new field of collision dynamics in extrasolar systems. The prize wasn't for finding a planet. It was for finding that planets can be destroyed, for showing the universe was more violent, more dynamic, more interesting than anyone thought. At the reception, a young graduate student approached Hartwood, nervous, eager. Dr. Hartwood, I wanted to say your work inspired me to switch fields. I was studying stellar astrophysics, but after reading about Alpha Centauri, I moved into planetary dynamics. I'm starting a PhD on collision simulations next fall. Hartwood smiled. That's wonderful. Where MIT working with Dr. Brennan. He's an excellent advisor, demanding but excellent. The student nodded. I know, but I want to understand this. Collisions, orbital chaos, how systems evolve. There's so much we don't know. There is. You'll help us know more. After the student left, Hartwood found a quiet corner, looked out at San Francisco skyline. Lights spreading everywhere. Somewhere out there, people were looking up, wondering about stars, wondering what existed beyond Earth. And now when they wondered about Alpha Centauri, they had an answer. Not simple, not there's a planet, but something richer. There were planets, past tense. 2 of them locked in orbital dance for billions of years, until June 2020 when they collided in catastrophic merger that vaporized atmospheres and left only cores. Those cores still orbit, still spiral inward, still carry memory of what they were. And someday, 47,000 years from now, they'll merge again. The universe is patient. Violence operates on timescales dwarfing human lifetimes. But it's always there, always happening. We're just learning to see it.